All right, so the actual sim can just live in here too. I mean, we have our particle sim up here. We can just put our pyro sim down here. So make a dot network. Have this go into that. We'll call it like, oh, pyro net. Like a cool cyberpunk thing. Nothing in here, not like the particle one last time. So let's make our type sparse. Like so. And we want the pyro solver sparse. Type sparse again. We want this smoke object sparse. You know, the original ones are still in here. If you typed pyro, you'd have pyro solver and pyro sparse. The sparse solver doesn't completely replace the pyro solver. The sparse solver is great when you have things that are sparse. Like we're going to have these trails with huge gaps of air between them. Explosions in general would also benefit from sparse because they tend to, let's say it's like a mushroom cloud, you have a lot of area under here that's not filled in. The sparse solver will usually be faster. Let's just go ahead and hook these up. It will, but the original pyro solver still works fine, and it actually is accelerated with OpenCL, which is the thing that uses the GPU cores together with your CPU to do stuff together, which is nice. The sparse solver actually doesn't support OpenCL, or at least it doesn't with the sparse capability. So, you know, turn that off again and have this be all on the left side. Sorry, I'm like saying and thinking two things at the same time. I'm just trying to say there are reasons to use the old pyro solver still, although most of the time you will probably want to use the sparse solver. It's pretty fast. Let's see what we get. Let's do a volume source and start bringing in what we created, and we can start to see what makes the sparse solver different. So go to sourcing, which apparently is the third one here. And we have our volume source here. Say the first context geometry, which again is this input, is our input. And we need to switch away from source smoke and then switch back to source smoke to actually get it to populate these things here. We have a density field. We don't have a velocity or temperature field, so only the density one's going to do anything. So we press play. There you go. So we can already kind of see, oh look, we didn't even have to set up the dimensions for our smoke sim. Remember we had to do that before in volumes 2 with the regular standard pyrosim. It will automatically resize the maximum bounds for us. That's cool. But even better than that, if we have a frame like this, not only did it resize to this, it's actually only simulating the areas right around that. How do we know? There's a guide on the smoke object called active region. If it looks super dark like this, go to smooth shaded, and then it'll be bright again. This is actually the only region that's being stored in memory. Everything that's in this jagged blue area. So it's not even that it's simulating everything in this white box. It's only simulating everything that's in these blue areas, which is obviously a massive improvement. There is, in fact, I think, just looking at this, more unused area in here than used area. So only this needs to be stored in memory, and only this needs to be actually simulated. Normally, the fluid simulations like this, because smoke is a fluid, has to do these huge matrix calculations to figure out the pressure and whatnot. And now it will do it only in these little smaller areas. So we have it. So where is it? It's where the smoke is, and then it's expanded a few tiles out. These cubes are tiles. So that's pretty cool. Go to the pyro sparse. Turn off this dissipation. We'll make our own microsolvers. But there you go. Here it is just accumulating. So this is more usually what your sim will look like, where it's not necessarily broken apart simulation areas, but it's still, it's one continuous area now, but it's still getting away with not doing all of this area, all of this area, all of this area. It's a huge win. Even all of this area, looking at it from the top. So again, it's practically doing half of the work than it would have had to have done otherwise. Why might you still want to use the old pyrosolver? One of the main reasons could be if you're going to just have everything, if you just have, let's say, a whole scene of smoke, like you're in a room where, there's like knockout gas is coming in or something, and you're just going to have smoke everywhere, it can be more efficient to not use this. Because again, this doesn't use OpenCL. If you turn on OpenCL, there is an option for it, it will throw an error and say, hey, listen, you can use OpenCL, but I'm not going to do the sparse solving anymore. Sparse solving is not supported with OpenCL disabled. So it'll still do almost like a regular pyrosim. So there you go. So if you want to use OpenCL, you're going to want to use the regular pyrosolver. So that's a big reason to use the regular pyrosolver, which is why I'm not going to call it the old pyrosolver. It's just the dense pyrosolver. This is the sparse pyrosolver. Similarly, if I had like a ship coming in, let's say from over down here, like a big meteor is coming in here, normally in the standard dense pyrosolver, it would be pushing all of the air in front of it. But if I have a collider in here, unless I add that to the sparse sim explicitly, it doesn't know about anything happening out here. So I could have a big ship moving in here thinking that it's affecting the velocities, the air being pushed ahead of it, but it won't be because it's not in the sim. And you can explicitly add it to the sim, but then again, you're starting to lose the benefits of it being a sparse solver. And if you're not taking advantage of the sparsity, then it might actually end up being less efficient than the dense solver. But again, to reiterate for the 100th time, much of what you're going to be doing these days probably going to benefit from using the sparse solver. So this certainly does, so we'll just keep doing this. So we talked about that to death. We might want to add temperature into this, and we don't have a temperature field, but we can just reuse our density field. So I'm going to say density. Actually, before I even do that, I did want to show you something else, another little fun gotcha. Sometimes, especially at a higher resolution, so here I am going to 0.02, watch what happens. Well, that sucks. Obviously, we know that this doesn't just stop here. It's supposed to go much higher up. What's happening? Well, when this is at its normal size like this, the tiles themselves are bigger. So the expanded area is bigger. So any given frame, when we source our next bit of volume, we're sourcing our next bit of volume into an active region. That's good. So it sees it and then expands it more. So our density is being added always into an active region, and it's allowed to expand just in time to always be accommodating the next bit, and there's no issue. But when our voxels are small, the tiles are smaller. Again, the blue cubes are the tiles. But our particles that are sourcing are still moving as fast as they've ever been moving. So what's happening is it's trying to source here, 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 but it's not sourcing into an active region. So it's not being seen. So that's why it's broken. All that is to say, always have enlarged fields to contain sources on your volume source, and their problem immediately goes away. What does that mean? It means when it tries to source into a non-active area, simply make that an active area. This should pretty much always be on. I don't know why it's not on by default, but that is a gotcha for you if you're trying to get your feet wet with the sparse solver and you don't know what that is. So now you do know, which is why you're watching this lesson, and there you go. So now it will always work, and that's awesome. So I'm going to go once again back to the big voxels though, just so we can work quicker. Temperature, let's just use the density, incoming density field as temperature. So now we can see the buoyancy of the heat making it go up. It's going up quite a bit. It's quite hot. because when we made this source on here, we said everything is times 10. So the voxels themselves, their highest values are probably around 10. So the temperature is also 10. That's quite hot. So what we can do is we can just say, let's multiply it by 0.1 on the way in. So we're still getting the full density, but the temperature is only going to be a tenth of it. So you can see already immediately it's not moving nearly as much. It's still moving though. It's still adding a nice bit of extra motion to give you the sense that whatever is emitting this smoke is like some super hot little thing that's then, the buoyancy is making it go up. So there you go. So that was a good chapter, right? You know about the Sparse solver now? Pretty cool.